Hey guys, this is Mr. Sal. We're going to look at domain and range in this lesson. I hope you guys enjoy it, or that it at least helps you out. So below is a formal definition of a function given two variables x and y. Y is a function of x if there is a rule that determines one unique y value for a given x value. Now those are pretty nerdy terms in order to understand what a function is. It's just saying that, for example, if I said x is some value like a, and then it produces a y value, let's say b. In order for it to be a function, if I see another time where x is a, I need to know that that y value is still going to be some b value, okay? So let's look at this in more, I guess, concrete terms, right? So if I said x was 2, right? Well, in purple right there, if y came out as 5, then in green, even though x is 2, I should get 5 again, all right? That would be functioning, or a function. If somehow x is 2, and then in green somehow y is something different, like 8. Well, now I'm not sure what value I'm going to get when I get x is 2. I'm not sure what value of y I'm going to get from that. So it's kind of like it's malfunctioning. So if we saw something like this where an x value produces one y value and then later on it produces a different value, then it is not a function. In the past, you guys have seen this maybe with a function machine, right? So you kind of have your input here, and then up here maybe you have your output, something like that. So it goes through this machine, right? And for example, if I put in, just like we did, well, we'll use a different value actually. Let's say that I put in 5, and then out comes 10, right? Now, if this machine is functioning, every time I put in 5, I need to get out 10. And then I know it is functioning. So, the next time I come to this machine, I put in a 5. And if it's functioning, I should know what comes out, because the last time I put in 5, a 10 came out. So, a 10 will come out. And then I know it's functioning, or in other words, this is a function. On the other hand, if I put in the 5 in this machine, but then for some reason out comes 4, okay, that's a little weird. That's not what I expected on this. So I would now say that this machine is no longer functioning. It's no longer a function. I mean, think about it like this, right? Like a microwave. Like if, let's say that I put in like a hot pocket, right? And I warm this thing up, and then out comes just a really hot pocket. Now we can debate on the actuality of a hot pocket coming out of a microwave because it's been nuked. That's not the purpose of this, because if you put it in a hot pocket, out comes a hot pocket, right? Well, from this machine, or microwave, right, if I were to go to it, and instead of out comes a hot pocket, maybe a burrito comes out. Okay, now I'm really worried, right? I've got something coming out of this microwave that was highly unexpected. Because I put it in a hot pocket, I would expect a hot pocket, not a burrito. Now this microwave is certainly malfunctioning. I probably wouldn't eat that burrito, but probably submit it to science. Now I hope that example kind of made sense right there, right? In terms of if something is a function or not. On the other hand, we do need to acknowledge the domain and range, okay? So the domain is just a list of all the x values, but remember, in these lists or sets, we don't actually list anything that happens more than once. So if I see repeats, I only list it once in the set. The range is the list of all the y values, or is the set of all the y values. But once again, if it repeats, I don't list it again. So on this problem, we're going to list the domain, but we need to be careful, all right? Because whenever we make lists or sets, we need to make sure we use fancy brackets. So the domain is all the x values. I see I've got a -9 there. I've got a -9 here, here, and here as well. So I don't need to list all of them. I only need to list it once. The domain is -9. Next up, I'm going to list the values in the range with some fancy brackets. So we'll list these starting with the left one, 9, 8, that's different, so I can list it. 7 is different, I'll list it. And then 6 is different also. So the range is the values 9, 8, 7, 6. Now you could have used a different order from least to greatest if you wanted to, but it won't matter. It's still the same list. Now we should be curious if this one is a function or not, right? Well, to answer that question, we see that in this ordered pair, -9 produced a 9. In this next one, -9 produced an 8. Now, even though -9 is producing different values for these other two, that's enough information, just those two first ones, to indicate that this is not a function. Because if you put in an x value of -9, you don't know what's going to come out. It could be 9, it could be 8, it could be 7 or 6, but we just never will know. Alright, so when we look at different functions to see if they are actually functions, we only need to be worried about these if one of the x values repeats. Now in R, we have an x value of -4. There's no other -4s in that list for the x values or domain. There's a 1, there's no other 1s. There's a 5, no other 5s. There's a 7, no other 7s. And 16. Since none of these repeat, we know for certain that R is a function. For set S, on this one, I have a -1 x value there, but another -1 x value here. These two are producing different y values, so S would not be a function. Now for the other x values, it's still functioning, but for the -1, it's a malfunction, so that one is not a function. Next up, G. We don't have any other 0x values, but we have these two 1s right here. And also they're producing different y values here, which means that this one also is not a function. F, this has a -4. Now we may get that confused with 4, but they're not the same, alright? So we got to be careful with that. There's no other 2s, no other 4s, no other 8s, and no other 15s. So this means that F also would be a function. Alright, so let's determine the domain and range of this set of values. So the domain, again, we need some fancy brackets, and I'm just looking at x values. All I have are -2s. So there's the set of x values. Next up, the range. Again, we do need fancy brackets. It's all of the y values. I've got 6, 5, 4, and 3. And some fancy brackets to close that off. So next we got to determine if it is actually a function. Well, for all 4 of these, this -2 is putting out, or it's because it's an input of -2, it's putting out of the machine something different every time. And we never know which one it's going to be. I mean, we know it's confined in those values just based on this information that we have, but we never know which one is going to come out. So this one is not a function. Alright, now we need to look at root functions. Since even roots cannot have negative radicands for roots of expressions, the domain is all numbers that make the radicand greater than or equal to 1. So this is what we mean is the square root of x. We don't find the negative value of that, because this is really asking if you had the area of a square, and well, let's say that that's the x value. Let's say that the x value is -25. So you're saying the area of the square is -25. Well, what's the side lengths? So we could say 5 and 5, but the problem with that is that gives us an area of +25. Even if we make those length's negative, we can't have, or they won't result in a product of negative 25. So that means that no matter what value we have in the radicand, x, which represents all values, it always has to be, or the x value itself, always has to be greater than 0, but it could also equal 0. And that would tell us the domain of that function. So in this example, I've got the square root of 9 minus x. But in order for this square root to work, or give us any real values for the domain, I've got to have a 9 minus x that's greater than or equal to 0. Because as soon as 9 minus x becomes a negative value, it's no longer in the domain. It's some kind of strange imaginary value, which we don't really get to in this class. So to solve this one, we would subtract 9 from both sides. And again, this is the domain because we're looking specifically at the x. So I've got negative x is greater than or equal to negative 9. And this is going to take us back. Right here, I've got to divide both sides by a negative 1. Since I divided both sides by a negative, it's going to flip the inequality so that I get x is less than or equal to positive 9. But we want this in interval notation, so it may help to see the graph on this one. And at 9, we would have a closed circle. It is not eating the x, so it goes to the left. Now again, I use that specifically for the interval. I can see this line goes as far to the left as negative infinity, but it does stop at 9 going to the right, which is included because it's a closed circle. And that's all they really wanted on this one. The domain is that green interval. Next up, we're going to be looking at fractions. And here's what we know from fractions, right? If I have anything divided by 0, let's look at this as a number, like 5, that's going to be undefined. In fact, anything divided by 0 is undefined because if we look at the long division, right, 5 divided by 0, we're looking and seeing how many times 0 goes into 5. Well, how many zeros do go into 5? 1, 2, 10, a billion? Yeah, all of those. In fact, it's more than that. It's so many that we can't even count them. It's an infinite number of zeros going to 5. And they never actually end up reaching 5 anyways, which is why it's continually increasing. So that's why that value is undefined. Well, what this means is that in a regular fraction with an x in the denominator, even if I had 1 over x, in fact the numerator doesn't matter at all for now. In 1010 we'll see where x values are in the numerator and denominator, but we're not concerned about that right now. So from this one, the domain would be all x values that don't make the denominator 0. So as soon as x becomes a 0, then it's not part of the domain. So what does this mean? If we were to expand on that, x minus 2, well, x minus 2 is okay as long as it's not equal to 0. And that actually would represent the domain. Of course, we would solve that, which we're going to do in the next problem. So we're going to show the domain in 3 different ways, okay? First of all, again, the numerator doesn't matter. What I want is just the denominator, which in this case is x minus 4. Now remember, in order for this fraction to work, I just got to make sure that denominator, x minus 4, is not equal to 0. This is actually a form of an inequality. To solve this, I'm going to add 4, and this is the domain, by the way. And I get x, that zeroes out, is not equal to negative 4. Now this would be the inequality portion of it. Let me show the graph on this, okay? So at negative 4, here's what I know. X cannot equal negative 4. So that's an open circle. But anything to the left would work. Anything to the right would work. So how do I show this using an interval, which is going to be required on the homework? That red line goes as far to the left as negative infinity, but it stops at negative 4. And that's not included, right? Well, the red line also goes as far to the right as infinity, which is not included. But where did it start from? It started at 4, which also was not included. So to indicate that all these values are included as the solution set for the domain, I'm going to unite them or put an OR statement between those. So we've represented the domain all 4 different ways here, with the inequality, the graph, and the interval. Alright, let's do this one too, okay? So once again, we have that x plus 3, right? That's to the denominator. We don't need to worry about the 1, or whatever even the numerator is. We don't worry about that, okay? And I know that x plus 3, it just can't equal 0. So, solve this one. We're going to have to subtract 3 from both sides of this inequality. So that zeroes out. So x is okay as long as it's not equal to 3. Now, we want the interval notation for this one. Once again, we'll show it on the graph. At negative 3, it's not included, but everything to the left is, and everything to the right is. Because this is one specific value that x cannot equal. So, the interval, it goes from negative infinity, going to the right, it stops at negative 3, which is not included. And we're going to unite this starting again at negative 3, which is not included still. But going to the right, it stops or ends up going all the way to infinity. And that right there is our interval for this domain. So the last part of this section deals with evaluating functions, but it's going to show this a little differently, okay? So just to start out with, y is f of x. So before, when we saw equations like y equals 3x, like this, the difference is instead of y, we're going to see f of x equals 3x. Notice nothing changed on the right. The only thing we changed was the y value. If we use the same function right there, f of x equals 3x, but let's say that we don't show f of x, we show f of, I don't know, 2, okay? Well, this is saying, or replacing the x with 2, which means in the equation, we would also replace the x with 2. So that would be 3 times 2, and f of 2 would equal 6. Now, I should talk about the way it's pronounced or communicated. Up here, f of x right there, that's f and x. It's not f times x right there. It's a function of x. And that's because y is always depending on the x anyways. Y is what we call a dependent variable. So we can show it as a function. It's a function that depends on x. So down here what I've done is I've shown the function which depends on the x being 2, and I would find that that would be 6. Now this is a relationship of two things, right? So we're saying as we find or know a value of one thing, if it's related to another thing in a certain way, we can find it based on the other one, as long as it is a function, as long as it's functioning, okay? So up here, again, it's showing this f of negative 12 means x is negative 12, and then in the equation, whatever it may be, we replace the x with negative 12. So let's look at this example. Find, or when f of x equals 9x plus 2, evaluate f of 3. So this is the function right here, but we're replacing this x right here with 3, right? So you see how the x was replaced with 3 there? So I've got to replace the x in the equation with 3 also. From here I just evaluate this, and it's still going to be shown as an answer as a function. So I need that f of 3 as part of the answer. 9 times 3 is 27, plus 2, that would give us 29. So the full answer is f of 3 equals 29. Next up, we want to evaluate this function for these two values. So all I've done right here is rewritten the function, but with the x values in parentheses, right? So starting with a, f of 0 means I'm replacing all the x's in the equation with 0. From here, it's just an evaluation process. F of 0, 6 times 0 squared is 0, plus 0 minus 4, that gives us negative 4. And that would be the solution for f of 0. F of 0 equals negative 4. The next one has an x value that's 2, f of 2. So I replace all the x values on this one with 2. So I get f of 2 equals 6 times 2 to the power of 2 should give us 24. That's going to remain a plus 2 minus 4. And what do we get on that one? 22. So f of 2 would be 22. And that is how we would evaluate these functions based on them showing us the value of x in function notation. Alright, you guys, that does it for this lesson. Thanks again for watching. This is Mr. Sal. If you found that this video really helped you out, please like it and subscribe to the channel and just make a quick comment below. We'll see you guys in the next one.